We are now going to move into part 2 of our problem sets, which will be the analysis of a DC network. Problem number 1. In this problem, we are to calculate the current through each of the resistors in this DC circuit, using the branch current method of solution. The branch current method makes use of the superposition theorem, which states, in a linear circuit with several sources, the current through the voltage drop for any element in the circuit is the sum of the currents and voltages produced by each source acting independently. To start, I'm going to label all the nodes. There are 4 nodes in this circuit, as indicated by the letters Node A, Node B, Node C, and Node D. Nodes are junctions where 2 or more current paths come together. A branch is a portion of the circuit consisting of 1 or more elements in series. This circuit contains 2 sources and 3 branches, each branch of which is a current path in the network. Branch ABC consists of the power supply E1 and R1 in series. Branch ADC consists of the power supply E2 and R2 in series, and branch CA consists of R3 only. I'm assigning a distinct current and arbitrary direction to each branch of the network. I1, I2, and I3, these currents create voltage drops across each resistor, the polarities of which is determined by the assumed direction of the current and the passive sign convention. The polarity of the power supply terminals is fixed and is therefore not dependent on the assumed direction of current. Notice the words arbitrary and assumed direction. After the calculations are made, if the assumed current is minus, then the current will be flowing in the other direction to the assumed direction. A closed loop is any continuous connection of branches that allows us to trace a path which leaves a point in one direction and returns to that same starting point from another direction without leaving the network. Now we apply Kirchhoff's voltage law around each loop. For loop ABCA, or loop 1, remember Kirchhoff's voltage law tells us that the algebraic sum of changes in potential around any closed circuit path or loop must be 0. Starting at node A, voltage source E1 rises to a potential of 8 volts. Therefore, plus 8 and the resistor voltage change is minus 2I. For resistor R1, and it is minus 4I3 for resistor R3. These voltage changes, when added together, must equal 0. So we write that in the form of an equation, as you see here. The currents are the unknowns. For loop ADCA, plus 24 for E2, and the resistor drops the voltages by minus I2 for resistor R2 and minus 4I3 for resistor R3. These voltage changes, when added together, must equal 0. We write that in a form of an equation. Plus 24 minus I2 minus 4I3 is equal to 0. Kirchhoff's current law at node C tells us that I1 plus I2 is equal to I3. The 3 equations can now be solved by the elimination method. Firstly, by rearranging the last equation, we can clearly see that we can express I3 in terms of I1 and I2. Now, using the above two equations, I'm going to substitute for I3, which is equal to I1 plus I2. We now have two equations with two unknowns, I1 and I2, the unknowns being the loop currents. We could have gone immediately to these two equations to solve the problem. However, we did introduce a third equation and a third unknown by using Kirchhoff's current law, which, as you recall, generates the Kirchhoff current law equation at the bottom. This points out the fact that there are more than one way to solve or analyze a mesh equation. Solving for I1 and I2 will also give us I3, which is all just mathematics, and I'll leave that up to you to solve as a mathematical exercise. On second thought, I will walk through the mathematical solution for I1, I2, and I3. First, let me move these equations around to give me some more room for further calculations. Our first step will be to remove the brackets in the equations, which will give us 8 minus 2I1 minus 4I1 minus 4I2 all equal to 0. And removing the brackets from the second equation will give us 24 minus I2 minus 4I1 minus 4I2 all equal to 0. Collecting like terms in the first equations results in 6I1 plus 4I2 equals 8. And collecting like terms in the second equation results in 4I1 plus 5I2 equal to 24. Now I'm going to multiply the first equation by 5 and the second equation by 4. This will allow me to get rid of the variable I2 by subtracting the second equation from the first, which will leave us with just one variable, I1, and the equation 14I1 is equal to minus 72. This results in the solution for the variable I1 being minus 5.124. Now, in order to find a solution for I2, we will bring back one of our previous equations, which is 6I1 plus 4I2 equals 8, and plug in our variable for I1, which allows us to mathematical manipulation, to manipulate now to easily solve for I2, which is 9.715. We can now find I3 by plugging in the values that we have just solved for I1 and I2, 4.575. You'll notice that we found that I1 was negative. That was negative 5.14, which means we assumed the direction of current flow in the wrong direction originally. So that current is actually flowing in the opposite direction. Before closing, I want to let you in on an early Prime Day sale at Jackery Canada Solar Generators. Simply go to this web address, which will allow you to get in on up to 65% savings. This brings us to the close of this section of the problem and its solution. If you want the full range of problems and their solutions, you can find them by going to my stand store at this web address. And finally, my newest course that I just added, Bridging the Gap Between Theory and the Practical. This course was developed specifically to solve the pain point of those newly introduced to the power industry. Whether you're an engineer, technologist, or electrician, this course is designed to give you a preview of what's ahead of those just leaving the halls of book learning and entering into the electrical power industry.